Okay, so the question was about log and base 0, and that's a good question. So for example, let's just try some things and see what happens in log base 0. So log base 0 of, I don't know, let's try 5 equals, what do you mean it doesn't work? Why is there a math error?
Because the calculators aren't smart enough.
Calculators aren't smart enough? Well, I'd like to think I'm smarter than the calculator, and I'm not smart enough to figure that out, so maybe it's not that we're not smart enough. Yeah, so let's just pretend that this existed. Let's pretend that there was such a value, and we'll call it x. That means that 0 to the x equals 5. So that's a neat trick if you can do that, okay? But, so for the only thing that we can, well, I mean, I guess, can we say this? Will this work?
Infinity.
What do you think? How is 0 as a base connected to 0?
No, 0 will never be the thing that you get from exponent.
Well, if I have a number like 0 and I want to go like this, what can you say about that number?
Doesn't exist.
What do you mean by infinite? It can be anything, because we don't know what exponent you used. If I use exponent 1, 2, 3, 1.5, 6.7, pi, whatever you want, it's still going to end up to be 0. So there is no consistency there. There's no number we can pick that they're connected. Yes?
Why cannot be negative or negative by the
That's another problem. If we had a negative, that would throw another wrench into this, because if it was a negative number, it would be 1 over 0, which, boom, your calculator explodes and you get to go home sick for the... No, never mind, you don't.
Yeah.
But, okay, so that's why we don't talk about logs in base 0. They have strange definitions and won't work for us. Okay, let's take a look at another example here. So, it looks complicated what we're looking at. So what we're going to do is we're just going to pretend for a second. Let's do one piece at a time. So I'm just going to cover up the 10. Can anybody evaluate that? If it's hard to see, this is a 10 and this is 100. Yeah, so this piece here would be a 2. So what would the result be of the whole thing?
10, 100.
100, right. Okay, let's see. Can we do it again? So this one is 5. This is 125. Yeah, that exponent is 3. So what do we end up with for the whole thing? 125. Okay, can anybody make a prediction?
43.
Yeah, how'd you make the prediction, Robbie? You're right.
What's your call?
Your genius is just so beyond you that it just leaps out sometimes. You can't explain it. Fair enough. You're right, it's 243. So the way it works, if you think about it, well, can anyone explain this? How is it that it's just working out to be the second number? Exactly, it's an inverse function. So if the function is exponent and the inverse is log, a function and its exponent undo themselves. So that's what we have here. If you take the function, which is the exponent base a, and the inverse, which is the log base a. So this is f of x, and this is the inverse. Then that means all you're going to be left with is just x. Okay? So if you ever see that sneak into your work, you can safely simplify it by just ignoring the log and the exponent. They disappear. Okay? So let's think about it the other way around as well. If I have 10 squared, well, these ones are even easier, right? Because the logarithm is trying to figure out what exponent of 10 is 10 squared.
2.
Yeah, it's 2 because it says it right there. It's the second exponent. What exponent of 5 is 5 cubed? Yeah, it would be 3. And it would be 5. So again, it's because this is the function and its inverse. You combine them. So when you combine a function and its inverse, everything disappears except for x. Okay. So why do we need logarithms, right? Why should we bother to study these things? So far, it seems so simple, like, we can guess a lot of them. But what if we had an equation like this? 10 to the x equals 300. Or sorry, 30. Yes, I know. I'm seeing doubles, I guess, right now. It's not as simple to solve, right? Because we don't know. I mean, I'd be really impressed if you could guess what that is. But my best guess would be I'd tell the person, well, it's got to be more than 1, but it's got to be less than 2. right? It's somewhere between 10 and 100, so it's got to be between 1 and 2. But if we rewrite this, trying to figure out, we want to know what's the exponent. So if I want to know what an exponent is, what's the tool? Logs. That's what logs tell us. Logs tell us exponents. So if I rewrite this, I'm going to have log in base 10 of 30 equals to x. Okay? This is something we can put in the calculator. The log in base 10 is known as the common log. Okay? Log in base 10, I don't know if it's called the common log because 10 is such a simple number and our number system is base 10. But you get things like Richter scale. Richter scale is in base 10. pH scales are in base 10. Bells, like the loudness, decibels and things like that, those are base 10. A lot of the stuff that's used in scientific community is also a base 10. So we call that the common log. And that's the button on your calculator that just appears as log. So what value would it be for x? Try it in your calculator, see what you get. 1.47. Okay, so try it. Try 10 to that exponent. How close does it get? I mean, you're going to have to round it at some point, right? But do you get back to 30? So 10 to the 1.477. Was it right? Good. It's a hard number to come up with without the calculator to help you do that. So, okay.
You actually learned how to do it without the calculator?
Not like that. Before they had calculators, they had gigantic tables, and you had to look things up in tables. So fortunately for us, we don't need to do that. We've got good calculators now. Okay, solve what's it called? It's a math class. It's an equation. Okay, so solve 3 to the x equals 10. Okay, so we've got a technique now. So how can we, we're asking about an exponent. This is going to be log of base 3 of 10 equals to x. But where's base 3 on your calculator? Right? We look at it and we're kind of like, oh, well, we'd have to have a pretty large calculator if we had every base that we wanted to work with on there, right?
No, I have it.
You have log base 3?
Like this.
Oh, you have a magic calculator button. Okay. That's nice, but for most of us, we don't. And the reason why is we don't need it. There's only one other button on your calculator which has another log. It's the natural log. And it is the log in base E, which is Euler's constant. Okay. So if you want to sound funny, go to university and say it's the Euler's constant. And then your professors will laugh at you, I'm sure, but maybe we'll all be in on the joke, so they won't laugh at you, they'll laugh with you. This is the only other base on your calculator. It is another very common base that is used. When you get to calculus, which for some of you, that'll be next year, log in base E is very, very common. Euler actually, I'm not sure, actually I would be shocked if he didn't know the applications that came from this constant. But basically, things which grow continuously, whether it's, say the population growth, whether it's, radiation, decay, there's so many applications of things which grow in a continuous manner. And this is the number that they grow by when they're continuous. So without going into a huge discussion about exponential growth, this is the next most common number that you'll run across. So that is the ln button on your calculator. Okay. ln. So some people say that as ln. But anyway, it's the natural log. So how do we solve the original problem? 3 to the x equals to 10 if we only have two bases? Well, I'd like you to try evaluating these using your calculator. Okay, so for example, you have a log button, so try log 27 over log 3 and see what you get. So what did you get for the first one? 3. Okay, what about log 47 over log 7? Yeah, you get 2. Make a prediction for me. Can you do that prediction without your calculator? What's log 625 over 5 going to be? 4, yeah. So here's what you're actually seeing. It's actually the calculator doing this. If you think about the pattern here, this would be the same thing as log base 3 of 27, right? This would be the same thing as log base 7 of 49. This would be the same thing as log base 5 of 625. So now we have a way we can try to link these things together in order to change bases. So you didn't have log base 3 in your calculator, but by doing this, you were able to do a log base 3 calculation.